Yes, thank you. So it's late in the day. There'll be plenty of demos in this, so plenty of things to entertain you by going wrong, maybe. Anyway, this is a joint work with Mario, who sits over there. It's a cryptic title, so I'll start by explaining the title. GOL here means Conway's Game of Life. And if you're not up to date with what Conway's Game of Life is, I'll let you know. I'll spend the first part of the talk explaining that. So then, Conway's Game of Life in GOL. So Conway's Game of Life simulated in Conway's Game of Life, and all of this verified in the HOL for prover. So GOL and HOL. Okay. So this talk will be two parts. First, I'll talk about what is Conway's Game of Life and various things you need to know about it for understanding the rest. So let's start with what is Conway's Game of Life. And rather than going directly through the rules, I just want to show you what it looks like, because there. This is very slow, unfortunately. Okay, so here I have written ITP in a 2D sort of grid, and the cells that are white are considered live, and the cells that are black are considered dead. And time goes forward in discrete steps. So now I take a time step forward. Looks like that. Take another step, another step. You can see it's a mess, right? Okay, but now you know that it's a 2D grid and time goes discretely forward. So let's look at what the actual rules are that determine what's going on here. So we define a goal state, or we consider a goal state to be a set of integer pairs. So if an integer pair is in a set, then it's considered live in that state. So the next state function, so given a state, we can take another, for a location to be alive in the next state, if it is alive in the current state, then we need to count the number of adjacent cells that are alive. I'll get to that in a moment. But if the adjacent cells, the number of alive adjacent cells are either 2 or 3, then this cell is live in the next state. If it's not live in the current state, then for it to be live next time, it needs to be exactly 3 that are alive around it. So what's this live adjacent then? Well, here's the definition, but you should think of it like as the 8 squares, 8 cells that are immediately around ij. So we count how many live are in there. So now let's go back to the simulation and try to understand it better. Why was it doing what it was doing? So if we go back to the start. Now let's have a look at one particular cell, like this one. It has exactly 3 live neighbors. So it should go, when I click the next, it should become live. And that's it. Yes, it became live. If we go back, one cell here has way too many live neighbors. It's going to go, it's not going to make it. Take a step and look over there. Okay, so it's not. Okay, so that's the rules, and they're very simple. And now I'm just going to run it for a while. And you see it's just a mess, but eventually, yes, now we're seeing an interesting figure coming out here. So this one, look at that one. It has a specific behavior. If I go forward, it repeats. And it keeps on going and just sort of self-sustaining. Yeah, so this is called a glider, and it's a kind of spaceship, it's called. That's the terminology. And if we run this, oops, over Zoom, this is not going very well. Anyway, gliders, yes, I can't show it there, but gliders, you see, one can consider them carrying signals. Okay, so I have shown you the rules of GOL, have showed you gliders. Gliders are a kind of spaceship. They're called spaceship because they move through space, I guess. And now, what about useful collisions? What's that all about? Let's have another demo. So here we have two streams, and if I go forward, yes, what happens? They vanish. So if I run it, oh, this running over Zoom doesn't really work very well. But basically, you see they take each other out. And this is actually very useful computationally. They take each other out cleanly. Now, what happens if I do a little change to this? I've just put it slightly differently there. And now if I go on, yes, we're back to the mess. It's a complete mess. So you see, everything's very delicately set up. And if you get it right, then it looks very nice. Otherwise, it's a mess. So why do I call this a useful collision? Well, if I have multiple streams, let's see if I can get this to go far enough. So this one cancels out that stream. Oh, no, this was with the bad. I can remove that one. Is it visible? Kind of. Yes, now there's another stream coming. And now if I have two streams, oops. What happens is that if we eventually let it go, the first stream protects the other one. Okay? So if both of these are on, this one survives. If only one of them is on, they're both killed. And if neither exists, well, none of them are getting through. So the point is, if we consider the existence of this stream as a signal on, and this one as an existence, that this exists, then it's two Boolean signals. If they're both true, then this computes AND. Okay? Yes? Okay, so the way I got into this is that my PhD student, Andreas Löw, pointed me to these blogs where Nicolas Carlini was building logic gates in Conway's Game of Life. I'll show you a bit of his blog very quickly. Here. I'll just show you his AND gate. So here, he doesn't use a bit quick in this animation, but it's the same concept. Oh, well. It's the same concept. These are now lightweight spaceships instead of gliders, but there you do see gliders go past. As long as both of these are on, the output is on. If one of them is off, then there's no output. So it's an AND gate, but this time with signals that instead of traveling diagonally, they travel horizontally or vertically. Okay. Could also, well, let's not show it here. Let's go ahead. So, okay, so one can build these logic gates. And then I was thinking, what's the sort of interesting circuit to build in Game of Life then, if we have these logic gates? Well, one question is, can we build a megacell circuit in GOL such that if the entire space is tiled with these kind of megacells, can the joint behavior simulate GOL? Can we make a circuit that is simulating one cell of Game of Life? And so then if you tile everything, the whole thing is a simulation of Game of Life. Can we that way have GOL in GOL? And this is not like, this has been done before, but not in a verified setting. So The answer is, of course, yes. And the challenge is to make such a megacell that has this behavior of behaving exactly like a GOL cell. So how do we build such a circuit? Well, here is our design. I'll explain it a little bit and then show an animation. So first of all, what is this? What is this supposed to mean? Well, each one of these is a gate. So that's an AND gate, just like we saw in Carlini's blog. These are just wires, turns, that's a NOT, an OR, and these things are half adders. So they compute the XOR and an AND. And by the way, yeah, these mini cells are 150 by 150 GOL cells, and the whole thing is 21 by 21 gates. Okay, so how does this work? Well, here we have a latch which contains, is this cell alive or not? It has one Boolean in it. And it's just made up of normal cells. It's not some special thing. It's just normal gates. So that's an OR, an AND, and it goes around. It remembers by sending the signal around. Well, to then compute the next state, what this does, it communicates its state to all the neighboring cells. You see here it goes out, there it goes to the other neighbor over there, and then we have here it communicates and here it communicates. So it sends its own state to all the neighboring cells, and from the neighboring cells it gets their input. Are they on or not? And so that's where these half adders come in. We collect all the inputs that come from the neighboring cells and just count how many are on. So we add these up, we add the inputs we got there, we keep on adding things, and now we've summed up all our neighbors, and then we check based on our own state whether we should be on in the next state or not. And that's the little circuitry here, and then it updates the latch. And this is all clocked by a circuit that just makes a signal go around and round. But let's animate this. So Mario made this cool animation. If zoom controls would get out of the way. Oh no, a massive zoom. Okay, so there's a lot of things happening here. Here's the latch, and you can see, so the colored blobs are the stable signals. The not colored are not yet stable. So here's always stable, and then now this is producing out a stable signal. And let's just reset it. So it's producing a stable signal, and it's communicating it to the neighbors. Here it's getting a stable signal in, and that is going then, the adders are doing their job. The adding, and then here we're going up. The stable signal arrives to the latch, and the next clock cycle starts. And the clock itself is this thing that's running away over there. It's that train of on going around. And that's the one that, when it comes to the top, it's going to feed in a clock signal into the latch at just the right time for it to tick to the next state. Okay, so that's how this works. Yes. Okay, so let's do verification of this then. First of all, I got into this because I saw Carlini's blog, and I thought, I've never seen this kind of thing done in an ITP before, and I don't know how to do it. So let's just think about that and how can we do it. So first, I started by thinking, why is the gates correct? Why are the gates correct? So then I developed this symbolic simulation simulator outside of HOL. The simulator is here. So when we normally run these, we run them in concrete mode. But here is a symbolic simulator. Let's see if the animation works through zoom. So you see, things are colored rather than black and white, and that's because black is again false, and white is true, but the colored are other things. So here we have, for instance, the variable b2. Here we have the variable b3. And over here we have a, a2, and a3. And what do I have over here? Is the variable expression, is the expression a and b. So this exists if the variables, you should think of this as, there's a big, all of these are Boolean expressions. And so this exists if both of those are true. Otherwise, it's just not, doesn't exist. And here we have mid-collision, so you have all sorts of mixtures of things. So, okay, so this allows me to get a sense of what's happening here without running all different cases. This is running one simulation, but getting all the results in one go. Okay, this is only part of the story, though. Now, though, the interesting thing is that there's some sort of repetition here. So if you now look, this is the answer A4, B4. And if I press this, when I do run, it just runs one step, one step, one step. But if I run 60, remember this is A4, B4. If I run 60, it actually did 60 steps of simulation, but the image looks identical. The thing that has changed is that this is A5, B5. So it did run it, but we come to an exactly the same picture. And now it's a fixed point. So the conveyor belts come in with new values, and the conveyor belt out is producing nicely the next sort of step in the conveyor belt. You can see this if we reset. If we run 60 initially, you see it's doing that, but now we are at a fixed point. Okay, so this is crucial to the verification proofs, and now I should hurry on to the verification proofs. So now moving on to being inside the ITP. First of all, we need compositional reasoning about game of life. The very first intuition is that patterns that are far from each other do not affect each other. So in the ITP, we define what an area of influence for a state. If two states have disjoint areas of influence, then you can calculate the step of the combined state as the separate steps. Great, that's very directly the intuition from seeing one of these simulations. But there's more, because we do need gates to communicate. They're not going to completely stay separate forever. A gate hands over a signal to the next gate, hands over one of these spaceships. So in the ITP, instead of proving things directly over step, we prove most of our properties about IO step, where IO step takes configuration as input. It makes sure that the state we were given is within its area that it owns. Then we take an actual game of life step, and then we get an S2. We check. This is a way of making assertions. If we take S2 and carve out this assert area, then we require it to have the assert content. We can also delete things from the resulting state, and we can insert things. So this is where we check that the output is what we want, then we delete the output, and we can also insert new input. Okay, so this now we have IO steps. Or one IO step, but we can also lift this to many steps. And now instead C is an infinite stream of configurations. So it says at this point we're going to get input, at this point we're going to get output, here's an assert about that, and so forth. We're not actually interested in the final state. We just want to show that a run is possible. So a run for an infinite stream of configurations from an initial state S is possible for any number of k. So this we write like this. There is some final state at that after k steps. Yeah, we can run without error. Okay. But now we need to have also, what does it mean to have a circuit do this? So we instantiate, or we build on top of run, we build this circuit run, which inserts the modifiers or the configurations for a circuit. There's some well-formedness conditions too. I won't go into the details of this, but I want to show you what a gate specification looks like. A gate specification looks like this. First, these coordinates are not GOL coordinates. They're in a larger grid. This says what part it owns. This is the input. Here's an at this location, this larger scale, you will have an eastward going stream of that's given by a stream of Booleans given by A, and at this location, from that location, you get input traveling north, and that's another infinite stream. And here's the output. At that location, it produces an output going east, which is A and B pointwise, but delayed by 5 steps both. Okay? So as a picture, this looks like this. You see -1 and 0 is there. 0 and 1 is here. B going north, this going east, and 1, 0 is there, and the combined stream is coming out with that delay from the inputs. Okay. So how do we prove a theorem like this then? Well, the answer is that we first define a symbolic simulator for that runs circuit I/O step. And then we use an external program to find one of these fixed points that I was showing you graphically. Once we have such a fixed point, we run the symbolic simulator for 60 steps inside HOL, and that way gave a confirmation that that is indeed a good fixed point. And from that, we can prove that for any run, we will get this kind of spec. Okay, that's only part of the story. We also need to compose circuits. So, and here's the circuit composition theorem. It looks big, but ignore the middle part to start with. If you ignore the middle part, then it's very neat, because it says, suppose you have one circuit and another circuit, and the areas they own do not overlap. Then the output is just a union of all the components from both the circuits. That's pretty neat. What's this mess about then? This mess is about when you have these jigsaw puzzle pieces. If we go back, you see they're not squares. They have these protrusions and like that. And you can't have those overlap. So that's why this is saying basically you have no, it doesn't sort of go into the other one. In practice, this is not a big deal. Okay, so let's have a look at a composition example. Suppose we want to compose an AND gate and just a direct wire. So we have the AND gate spec like we had before, and the wire looks very similar, except that it doesn't have the second input, and it just sort of duplicates the input as an output, but at a later time, 5 steps later. Okay, first thing to compose these is that we have to translate this one, because both of them occupy the same spot around 0, 0. So we can add 2 to the x values throughout, and then we've translated it to the right place. And now we can use our, we substitute also, we want this to match the output there, so we instantiate it, and now we get this sort of, because that was A with 5 delay, so we get it outside. Now we can compose these with the composition rule, and as a picture it looks like this. We just put them together, and now we have 3 inputs and 2 outputs, but crucially notice that one of the outputs is the same as the input. And that's this sort of join point here. And we have a theorem that says for any of such cases, we can just delete them from both the input and output, and that way internalize the whole thing. And what we get is this spec, which just occupies a bit more space and has slightly different delays. Okay. So there was a problem with the half adders. I showed you the half adder. It takes two inputs, produces an XOR and an AND, supposedly. And the problem is this. When you ran it through the simulator, we get the second output is definitely an AND. The other one is that XOR. And the answer is kind of. If you squint really, really hard, because ignore the superscripts, then this says A and not B, or B and not B. Well, that doesn't make sense. That's false. Not A and B. Okay, so it is XOR, but all these delays are messing it up. So we're too precise. And here's where Mario came to the rescue, and he defined the concept of stable signals, and then we got nice specs that are actually workable again. Yes. Okay, so we proved this. What that really means as a theorem is this: for any initial state in GOL states, we can build a megacell tiling such that if we run the step function this many times, then we can read off the states of all these megacells such that indeed it is exactly what a direct run of the GOL function would have produced. And that's it.